Have you ever looked up at the night sky filled with its countless stars and felt a sense of wonder? It is a feeling that connects us to our most ancient ancestors. They too looked at those same distant lights and asked the great questions. Where did all of this come from? How did it all begin? For a long time, we have had an answer that seemed to satisfy us: the Big Bang. It marks the start of everything we know, the birth of our universe, our stars, our planet, and even ourselves. It is a powerful and beautiful story of creation, a moment of incredible energy from which everything in existence blossomed. But our curiosity is a restless thing. It does not stop at a simple beginning. It pushes us to ask an even deeper, more challenging question. If the Big Bang was the beginning of everything, what was there before the beginning? This question can feel like standing at the edge of a great, silent ocean trying to imagine the other side. It is a place where our usual rules of time and space seem to break down. Thinking about a time before time can make our heads spin, like trying to imagine a color we have never seen. Yet, it is in asking these seemingly impossible questions that we push the boundaries of our understanding and venture into the most profound mysteries of existence. It is a journey not of finding simple answers, but of embracing the magnificent scope of what we do not yet know. For many years, scientists might have told you that asking about the time before the Big Bang was like asking what is north of the North Pole. But science is a story that is always being rewritten. New ideas, born from brilliant minds and fueled by incredible new discoveries, have begun to challenge this old notion. To understand what might have come before, we must first have a clear picture of the event itself. What exactly is the Big Bang? It is easy to imagine it as a giant explosion, like a firework in the silent darkness of space. But that picture is not quite right. The Big Bang was not an explosion in space, it was the expansion of space itself. Imagine you have a tiny, uninflated balloon. Now draw some small dots on its surface. As you blow air into the balloon, it expands, and all the dots move farther and farther away from each other. The dots are like galaxies, and the expanding rubber of the balloon is like space itself. This incredible event happened about 13.8 billion years ago. At that moment, the entire universe, with all the matter and energy it would ever contain, was squeezed into a point of unimaginable density and heat. This point was smaller than a single atom. It was a state so extreme that our current laws of physics cannot fully describe it. Then, in an instant, it began to expand. It didn't expand into anything because there was nothing outside of it. It was space, time, and energy all expanding outwards from that single, hot, dense point. It was the ultimate beginning of the universe as we know it today. In the first few moments after this expansion began, the universe was a scorching, chaotic soup of fundamental particles. It was hotter and denser than the core of our sun. As it continued to expand, it began to cool down. This cooling allowed the basic building blocks of matter to form. Protons and neutrons came together to create the nuclei of the first simple elements, mostly hydrogen and helium. For hundreds of thousands of years, the universe was still a foggy place, so hot that light could not travel freely. Finally, after about 380,000 years, the universe cooled enough for atoms to form. Electrons were captured by the atomic nuclei, and suddenly the universe became transparent. Light was set free to travel across the cosmos for the first time. This first light is something we can still detect today. A faint afterglow of creation called the cosmic microwave background radiation. It is like the faint warmth you can still feel from a fire that has gone out. The Big Bang theory is our best explanation for how the universe began and evolved into the vast, star-filled cosmos we see today when we look through our telescopes. It is a story supported by a mountain of evidence. For a very long time in modern science, the Big Bang was seen as the absolute beginning. The story of our universe started there, and there was no chapter before it. This idea came from working the story of the universe backward. Astronomers like the famous Edwin Hubble observed that all the galaxies were moving away from each other. The universe was expanding. If you imagine this process in reverse, like rewinding a movie, everything must come closer and closer together. Logically, if you go back far enough, everything must have been in one single place at one single moment. This moment was the beginning of everything, a point of infinite density known as a singularity. This concept of a singularity created a firm wall in time. Before this moment, our scientific theories, including Einstein's theory of general relativity, simply break down. The equations that describe the universe so well today give us nonsensical answers, like dividing by zero, when we try to apply them to the singularity itself. Because of this, many scientists concluded that asking about a time before the Big Bang was a meaningless question. It was like asking what is south of the South Pole. Time, they argued, was a property of the universe. If the universe began at the Big Bang, then time itself must have also begun at that moment. This idea was both frustrating and elegant. It provided a clear starting point for cosmology, the study of the universe. It allowed scientists to build a detailed and successful model of how the universe evolved from that initial hot, dense state into the complex structure of galaxies and stars we see today. The Big Bang theory became the cornerstone of modern cosmology, explaining so many of our observations, from the expansion of the universe to the abundance of light elements and the cosmic microwave background. The idea that there was no before was a perfectly logical conclusion based on the evidence and the theories of the time. However, science is never truly settled. It thrives on challenges and new questions. The idea of a singularity, a point of infinite density, has always been a red flag for physicists. In physics, infinity is often a sign that a theory is incomplete, that it is missing a piece of the puzzle. It suggests that we need a new theory, perhaps a theory of quantum gravity, to understand such extreme conditions. This discomfort with the idea of an absolute beginning has driven a new generation of scientists to peer beyond that wall, to ask that meaningless question once again, and to search for what might have happened before the Big Bang. One of the most mind-bending ideas to consider is the very nature of time itself. We experience time as a constant, forward-moving river. It carries us from the past, through the present, and into the future. But what if time is not as fundamental as we think? The late great physicist Stephen Hawking, along with his colleague James Hartle, proposed a fascinating idea. They suggested that if we could travel back to the very beginning of the universe, we would find that the distinction between time and space disappears. Time as we know it would cease to exist and would behave more like another dimension of space. This is often called the no-boundary proposal. Imagine walking on the surface of the Earth. You can walk north, south, east or west. If you head toward the North Pole, you can keep going north until you reach it. But once you're at the North Pole, you cannot go any further north. The direction north simply ceases to have meaning at that point. You can only go south. Hawking and Hartle suggested that time is similar. As you go backward in time toward the Big Bang, you reach a point where before ceases to have meaning, not because there was a hard wall, but because the very nature of time changes and blends with space. The universe, in this view, did not have a beginning in the traditional sense. This concept completely changes the question from what happened before the Big Bang to something much deeper. It suggests that the universe is self-contained. It did not need a creator or a prior cause to bring it into existence, just as the surface of a sphere has no edge or starting point. It simply is. According to this theory, the universe smoothly and naturally emerged from a quantum state where time did not exist as a separate dimension. The Big Bang was not a moment of creation from nothing, but rather the moment when time as we experience it emerged and started to flow forward. This is a challenging idea to grasp because our minds are so deeply wired to think in terms of cause and effect, which requires a past, present and future. But in the extreme realm of quantum physics, our everyday intuition often fails us. The no-boundary proposal is a mathematical concept born from the effort to combine Einstein's theory of gravity with the strange rules of quantum mechanics. It provides a way to describe the universe without the problematic singularity, the point of infinite density. It paints a picture of a universe that is finite in its history, yet has no boundary, no beginning and no end. Another captivating idea that, really challenges the concept of a single beginning is the cyclical universe model. This theory proposes that our Big Bang was not the first, and honestly, it will not be the last. Instead, the universe goes through endless cycles of creation and destruction. It is kind of like a cosmic dance of expansion and contraction, a grand story that repeats over and over again for eternity. In this view, our universe was born from the collapse of a previous universe. It is a powerful and ancient idea found in some old philosophies and now being explored with the tools of modern physics. It replaces the single linear timeline with an infinite loop. Imagine, if you will, a giant cosmic lung breathing in and out over trillions of years. In this model, our universe is currently in its expanding phase, the exhale. Stars are forming, galaxies are spreading apart, and the cosmos is growing larger and colder. But eventually this expansion could slow down, stop, and then reverse. A mysterious force, maybe something related to dark energy, could change its nature, causing the universe to begin contracting. Everything would start to pull back together, galaxies rushing toward each other in an event that could be called the Big Crunch. It would be the Big Bang in reverse, a cosmic inhale. As the universe collapses, it would become hotter and denser, undoing all the structures that had formed. Stars, galaxies, and even atoms would be broken down into their fundamental particles. Eventually, the entire universe would return to that incredibly hot, dense state, similar to the moment of the Big Bang. But instead of being a singularity, a point of infinite density, some new physics could take over. At this point of maximum compression, the universe would bounce. This bounce would trigger a new Big Bang, giving birth to a new expanding universe, and the cycle would begin all over again. This theory is appealing because it elegantly solves the before question. What was before the Big Bang? Another universe, one that looked very much like ours in its final contracting moments. It also avoids the problem of the singularity, replacing it with a big bounce. Physicists like Paul Steinhardt and Neil Turok have developed versions of this model, suggesting that these cycles are driven by the collision of brains or membranes in a higher dimensional space. While we do not yet have definitive proof, scientists are looking for subtle clues in the cosmic microwave background, the afterglow of our own Big Bang, that might be the faint echoes of the universe that came before. Perhaps the most mind-expanding idea of all is that our universe is not alone. It might be just one small bubble in a vast cosmic ocean of other universes. This is the concept of the multiverse. In this picture, our Big Bang was not a unique event, but a common one. New universes are constantly being born, like bubbles forming in a pot of boiling water. This idea arises from a theory called eternal inflation. Inflation is the period of super-fast expansion that scientists believe happened a fraction of a second after our Big Bang. Eternal inflation suggests that while this rapid expansion stopped in our pocket of space, allowing our universe to form, it continues forever in the wider cosmos. As this metaverse continues to stretch, small regions of it will randomly stop inflating and pop into existence as new bubble universes, each with its own Big Bang. If this is true, it means there is a vast, perhaps infinite number of other universes out there, coexisting with our own but completely inaccessible to us. We live inside our bubble and we can never reach out and touch another. It is a humbling thought, reducing our entire cosmos with its billions of galaxies to just one grain of sand on an infinite beach. It is a vast cosmic family where our universe is just one member among countless others. What makes the multiverse theory so fascinating is the possibility that these other universes could be wildly different from our own. The fundamental laws of physics, the constants of nature that make life possible in our universe, might be different in other bubbles. Some universes might have stronger gravity, where stars burn out in an instant. Others might have weaker nuclear forces, where atoms could never form. Some might be empty and lifeless, while others could be home to forms of existence we cannot even imagine. Our universe, with its finely tuned laws that allow for stars, planets and people, might just be one of the lucky ones. This idea helps to explain a deep puzzle in physics. Why are the laws of our universe so perfectly suited for life? This is sometimes called the fine-tuning problem. If there is only one universe, then it seems incredibly lucky that it turned out this way. But if there are countless universes, then it is not surprising at all. It is like having a lottery with an infinite number of tickets. Eventually, one is bound to be a winner. We find ourselves in a universe that can support us simply because we could not exist in one that could not. While we cannot directly see these other universes, some scientists believe we might one day find indirect evidence, perhaps as a bruise on our cosmic microwave background from a long-ago collision with another bubble universe. These ideas about what came before the Big Bang are more than just philosophical dreams. They are grounded in the language of mathematics and physics, and scientists are actively searching for evidence that could support or challenge them. Our most powerful tool in this search is the cosmic microwave background, or CMB. This is the oldest light in the universe, the faint afterglow of the Big Bang itself. It fills the entire sky, and by studying its tiny variations in temperature, we can learn an incredible amount about the early universe. It is like a fossilized photograph of the cosmos when it was just a baby. Scientists have built incredibly sensitive instruments, like the Planck satellite launched by the European Space Agency, to map this ancient light with amazing precision. These maps show us a pattern of slightly hotter and colder spots. These tiny fluctuations were the seeds that eventually grew into the vast structures of galaxies and galaxy clusters we see today. Physicists are carefully analyzing these patterns, looking for specific signatures that might point to one theory over another. For example, some versions of the cyclical or bouncing universe model predict a particular type of pattern in the CMB that would be different from the predictions of standard inflation. Another area of intense research is the search for gravitational waves from the very early universe. Gravitational waves are ripples in the fabric of space-time, created by the most violent cosmic events. We have detected them from colliding black holes and neutron stars, a discovery that earned a Nobel Prize. However, the inflationary period, or a cosmic bounce, would have created a unique background of gravitational waves that would still be echoing throughout the cosmos today. Detecting these primordial gravitational waves is incredibly difficult, but experiments like Bicep Keck at the South Pole are designed specifically to look for their faint signature imprinted on the CMB. Finding such evidence would be a monumental discovery. It would be like hearing the whisper of the universe's birth, or perhaps its rebirth. It could give us our first real glimpse into the moments before the Big Bang and help us distinguish between the competing theories. For now, the evidence is still inconclusive. Some initial claims of discovery have been shown to be caused by cosmic dust, not primordial waves. This is how science works. With careful observation, bold ideas, and rigorous testing, the quest continues with each new experiment and each new analysis of the data, bringing us one step closer to uncovering the true story of our cosmic origins. We have traveled to the very edge of time, exploring ideas that really stretch the limits of our imagination. We have considered a universe with no beginning, a cosmos that endlessly recycles itself, and a home that is but one of countless others in a vast multiverse. So, what happened before the Big Bang? The honest answer is, we do not yet know for sure. Each of these theories is a beautiful and compelling piece of a puzzle we are still trying to solve. The story of creation is not written in stone, but is constantly evolving as our knowledge grows. What we have is a collection of possibilities, each offering a different perspective on our place in the cosmos. This uncertainty is not a failure, it is an invitation. It is a call to the curious, the dreamers, and the next generation of scientists. The universe is not a closed book, but a grand, open story, and we have only read the first few pages. There are still profound mysteries waiting to be unraveled. What is the nature of dark matter and dark energy, the invisible substances that make up most of our universe? Can we finally unite the theories of the very large, general relativity, with the theories of the very small, quantum mechanics? The answers to these questions will undoubtedly lead us to an even deeper understanding of our origins. Think of it like being an explorer in a new land. With every step, you map a little more of the territory, but you also reveal how much more there is to discover just over the next hill. Our journey to understand the universe is just like that. Each new telescope, each new experiment, and each new brilliant idea pushes the horizon back a little further. The questions we ask today may seem unanswerable, just as the question of what stars are made of seemed unanswerable a few centuries ago. But human curiosity is a powerful force. It drives us to build, to explore, to think, and to never be satisfied with not knowing. So I encourage you to keep looking up, keep asking the big questions. Read about the latest discoveries from the James Webb Space Telescope. Follow the work of the brilliant minds who are dedicating their lives to peering into the darkness. The story of the universe is the story of us all, and the quest to understand it is one of the noblest journeys we can undertake. The cosmos is full of wonder, and its greatest secrets are still waiting for us to find them. Continue your own journey of cosmic discovery, for the universe is always ready to reveal a little more of its magic to those who are willing to look. Please like and subscribe to Cosmic Discover.